What we're going to talk about here is we're going to be looking at power series. Now, a power series is a very important element to bring into Advanced Higher because we're able to expand this and look at set types of power series, specifically the Maclaurin series. However, in order to do that, we have to understand the basics of it and understand what they mean, how we get them, and looking at sums to infinity. Now, the first thing we have to ask ourselves is, what is a power series? Well, we've encountered them before, we just don't know it yet. A power series is an infinite series that takes the format a0 plus a1x plus a2x squared plus a3x cubed, continuing on with a generic term of ar x to the r. Now, in each of these, the a, so the ar, that is simply a coefficient. That coefficient can be calculated or given to us dependent on the series we're looking at. This is how it's generally represented. We can represent this using our sigma notation, but this is how it's generally represented and written out when we expand that out. Now, one thing that we're going to be looking at is we're going to be looking at the behaviour of the series as r tends towards infinity. So as we get an infinite number of terms and we get it bigger and bigger and bigger. The question we want to ask ourselves is it divergent or is it convergent? That's the ultimate goal. We want to know if a series diverges or converges as we start to put in more and more terms, and we start to hope that we're going to get more and more accurate if it's a convergent series. So we have to ask ourselves, how do we do this? Well, first thing we have to think about is actually a series that we've done before. If we think back to when we did geometric series, so that was a series where the general term of un equals a r to the n minus 1, with a being our u1 term, so our first term, and r being our common ratio, with the knowledge that r cannot be equal to 1, because we have to have some sort of change in each term, we were able to say that divergence or convergence had one of two conditions applied to it. We had a limit, so it converged as n tends towards infinity if the common ratio r was between -1 and 1. So if our magnitude of r was less than 1 in this case. We knew it tended towards infinity, so it was a divergent series as n, the number of terms, tended towards infinity if r was less than -1 or r was bigger than 1, i.e. the magnitude of the r was bigger than 1. So we had these two conditions applied to the geometric series to calculate its limit if convergence was able to happen. Now, remember arithmetic ones, we couldn't do it. Arithmetic series just continually got bigger and bigger and bigger in terms of its size, so it had no limit. Now we can use a similar idea to our geometric series here as a method of devising the convergence, if we're able to do it, of a power series. Now let's imagine we take a generic series that we write out in this format. So the sum from r equals 0 to infinity of arxr, that's equal to a0 plus a1x plus a2x squared, continuing on with a generic term being ar x to the r, as we mentioned before. Now, similarly to a geometric series, if we look at the ratio of any two consecutive terms, we were able to get our common ratio. We can do that again here. So if we look at the ratio of two consecutive terms, un plus 1 over un, that would give me something in the format here, an plus 1x over an. Now we know that for that to have a limit, is n, the number of terms, tended towards infinity, i.e. we had more and more terms, we knew that as the magnitude of the common ratio was less than 1, we had a limit in the series converged. And that's the same principle we can apply to here. Because if we take the ratio of two terms, un plus 1 over un, and calculate the magnitude of that, if we looked at the limit as n tended towards infinity, so a number of terms tended towards infinity, if that was less than 1, that would mean, that's another way of writing, our common ratio, the magnitude of it, is less than 1. Which is similar to this, but this is just it written in terms of generic terms. So an plus 1x over an, again, that is what we would get for our common ratio if we looked at two specific terms. And again, as n tended towards infinity, if the magnitude of that was less than 1, so our common ratio was less than 1, we had a series that converged. So we can apply that principle to a power series in order to calculate whether it converges or not. And this point here, so where we have an plus 1 over x over an, the magnitude of that being less than 1 is n tended towards infinity. This also allows me to figure out any conditions I have to apply to the value of x I choose in my power series such that it has this limit and it exists. Because we will get that kind of question. We may only have a limited number of values for x where we have a limit for our series. We have to know how to calculate these values, and we have to know what they are. Now, this is a lot of jargon to throw at you. So the best way to look at this and figure out how to work it through and apply it is actually with an example. So I'm going to show you one now. Let's imagine I ask you to find the sum to infinity of the series s equals 1 plus 3x plus 5x squared plus 7x cubed plus a whole spiel of terms of the generic form 2n minus 1x to the n, all the way up to an infinite number of terms, and state the values for x for which the series is valid. Let's imagine I ask you that sort of question there. Now, the first thing I would always tell you to look at for this kind of question is look at the coefficients of each term. So I've got 1, 3, 5, 7. What that actually is a linear recurrence relation that I can write as un plus 1 equals un plus 2. So the next term is equal to the previous term with 2 added on it, and I can apply the condition that u1, my first term, is equal to 1. That there then gives me a linear recurrence relation I can use to calculate the coefficient of any term. Now, because of this, I can start to think of calculating the limit of these series using a fairly standard set method and strategy that could be familiar and applied essentially to a lot of different examples. First thing I'm going to do is I'm actually going to write down s, the sum. So I've got it here and I can manipulate it. So I know s, the sum, equals 1 plus 3x plus 5x squared plus 7x cubed, and it will continue on and on and on. What I'm then going to do is take the s and multiply it by x and write out a new version of it. So what I'd end up with is x plus 3x squared plus 5x cubed, and then again it would just continue on and on and on. Now, if I treat this as two different series here, label them 1 and 2, and I do series 1 take away series 2, so essentially s take away the xs, what I'm going to end up getting is 1, and then each of these is going to give me 2x to whatever power it is. I'd have 3x take away x, so I'd have plus 2x. I'd have 5x squared take away 3x squared, so I'd have plus 2x squared. I'd then have 7x cubed take away 5x cubed, so I'd have plus 2x cubed. So what I'd be able to say is my generic term anywhere along here would be 2x to the n minus 1. And that would continue on for the unlimited amount of terms that I choose. So there we go, we've got a general format for that series. What I'm going to do is let's say to ourselves, right, let's cut the series off and let's look at a partial sum. So let's cut it off at n minus 1 terms, so a spot on there. What we could then do, if I take s out as a common factor here and have it as Sn, so sum to n terms, what I know is that's going to be 1 plus 2x squared all the way up to plus 2x to the n minus 1. So it's going to go all the way up to that. Now each of these terms here has 2x to a power, which is great because that's almost a geometric series. The issue though comes in here with that 1. So what I can do is I can manipulate my series and write it as Sn bracket 1 minus x equals 2 plus 2x plus 2x squared, and then continue on, and I would have my generic term plus 2x to the n minus 1. So there we go, I've got a geometric series of the same format. However, I've added 1 on to get to this 2, so I've got to make sure I compensate for that by then taking away 1 afterwards. So what I've now got here is a geometric series, and we know that the sum to n terms of a geometric series is given by a bracket 1 minus x to the n over 1 minus x. Now for this one, a is equal to your first term, and in this case that is 2. So what I'm then able to say is that my sum to n terms times 1 minus x is going to equal this here with the a substituted in. So that's going to equal 2 bracket 1 minus x to the n over 1 minus x, and then take away that 1. Now, before I do anything else, I want this whole thing combined to become one fraction. So this minus 1, what I'm going to write that as is I'm going to write it as 1 minus x over 1 minus x and combine it all together. So what that then gives me is 2 bracket 1 minus x to the n, take away 1 plus x, because remember I'm taking away minus x, and then that's all going to be over 1 minus x. I'm then going to divide through by 1 minus x and add my sum to n terms is equal to 2 bracket 1 minus x to the n, take away 1 plus x, all over my 1 minus x squared. Now, that's great. That's the sum to n terms. But remember, for a power series, I've told you that we want n tending towards infinity. So we want a limit as n tends towards infinity. But for that to exist for a geometric series, which we've taken this to be, because it is, we know that the magnitude of r, my common ratio, has to be less than 1. To get the common ratio, we take the ratio of two consecutive terms. So for example, I'll maybe take 2x squared divided by 2x. Or I'll take 2x cubed and divide it by 2x squared. Bottom line is that my common ratio r is equal to x. So for this to exist, I know that my magnitude of x has to be less than 1. And if this exists and I think n tends towards infinity, what's going to happen is n to the power of infinity is going to become the dominant term, and because I'm taking my common ratio to be less than 1, which means x has to be less than 1, this is going to tend towards 0. So what that means then is therefore s infinity, so my sum as it tends towards an infinite number of terms, is equal to 2 bracket 1 minus 0, take away 1 plus x, all over 1 minus x, all squared, which I can then simplify and write as s infinity equals 2, take away 1, so I've got 1 plus my x there, over 1 minus x, all squared. And the values for x for which this series is valid, we already know, is the magnitude of x is less than 1. Or I can rewrite that as negative 1 is less than x is less than 1 itself. So there we go, we've answered the question. We found the sum to an infinite number of terms here for that series is given by that, and it works if I take x to be any value between negative 1 and 1. That's the general format. That right there is the familiar strategy we want to use when we find a series that looks along this line, and we get coefficients that follow some sort of linear recurrence relation pattern. Now, one thing I want you to know is we've been quite lucky here in that our common ratio has been x. A lot of times you'll find the common ratio won't be. So for example, if I had a common ratio r equal to 2x, I'm going to block this off here just so we don't confuse ourselves. What I would know then is that negative 1 has to be less than 2x, has to be less than 1 for the example at work. So I'd know if I divided through by 2 that my value for x would have to be somewhere between negative a half and a half. It's not always guaranteed to be this. So we have to make sure we're aware of that. We have to pick the right common ratio by looking at the terms when we get to this stage here. So bear that in mind. There's a few examples in the exercises video. Have a look at those and follow these generic steps and let's see how you get on. But bear that in mind for a power series. That's what we have to be able to do. The sum to an infinite number of terms, and let's see how we get on with that.